In this lesson, we're pushing into probability, so we're looking at linking sets and Venn diagrams and an alternate process called two-way tables to look at the probabilities within Venn diagrams and sets, as well as probability tables. We'll also have a little bit of a look into the addition rule, and that'll be our lesson today. So, first things first, we'll look back at our Venn diagrams, and we'll link them into a probability view that we'll be able to use. So if I set up this Venn diagram using A, B, the number in the universal set, so really this is a number of A and a number of B, then one thing that we can do is recall that in all cases, probability of an event, so let's say probability of A, will be equal to the number of A, so the cardinality of A, how many elements exist in that set A, over the number of the universal set. So number of A over the total number. Now this is a probability rule that you should know quite well. Now if we do that, then probabilities in here will be probability of A rather than number of A probability of B rather than number of B. This will be a probability of not A and not B, and so on. And the idea is that if we divide everything by the number in the universal set, then we'll convert into probabilities. Now it should then be that total probability, so the sum of all of the probabilities, is equal to 1. So instead of adding up to the total in that universal set, the probabilities will all add up to 1. So hopefully that makes sense. The second thing that we're going to look at is using two-way tables. Now, two-way tables are another way of looking at the same information within that Venn diagram. So if I draw my Venn diagram and I break it up properly into the major sections, so the major sections will be the intersection number of A and B, the only A sections, the number of A and not B, the only B section for the number of B and not A, and then the number of not A and not B. So those the number that are in the universal set but not within sets A and B. Okay. To look at this same thing in a slightly different way, we can set up what we call a two-way table. Now, in the two-way table, we can break it down to A and not A, and we're looking for the intersection between that and B and not B. Now, I did forget when I put in this A and not A that there's another important thing here, and that's that we're looking at a total. All right, so this is what our two-way table looks like. And to relate it to the Venn diagram, we're looking at intersections of each of these things. So everything's about intersections here. So this is A and B. This is A and not B, so this is only A. This is not A and B, so this is only B. This is our not A and not B. And these totals here are then, this is our number of B. This is our number of not B. This is our number of A. This is our number of not A. And then this is a number in our universal set. Now these should all be numbers, so they're all cardinalities. And the idea is that in this table form, they all add up. So we should be able to add this A and B and the A and not B together, and they should add up to give us a total number in A. We can do the same thing with not A and B and not A and not B, and they should all add up to the number in not A. And each column and each row should add up so that that number in the universal set is correct. So these two things allow us to look at both the cardinalities, or the numbers, and the probabilities if we want. The only difference with the probabilities is instead of adding up to that universal set, so if we're looking at probabilities, then that total will be 1. Obviously, if all our probabilities add up, then it's 100%, it's everything. Okay, so I'm hoping that makes sense. We can now build in probabilities as well as use two-way tables as an approach. The final little thing that I'm going to introduce is the addition law, and we'll use all of these in a minute. The addition law is this, and the idea is that we can find a law that relates the union and the intersection. Now, if I draw a Venn diagram, it should be nice and easy to understand. If we're trying to calculate that union just using our numbers or our probabilities, let's do it with numbers first. So let's say this is number in A, this is number in B. This is our intersection number of A and B, and the whole thing together is our number of A or B. So if I look at the number of A or B by adding the number of A and the number of B, it should be really obvious that if I say number of A, and let's make the number of B green, and the number of B, we add these two things together, that our biggest problem is that I've got two intersections. So this isn't A or B, it's not the union yet. These two add together, I've got the intersection times 2, so in order to even that back out, I have to take away the extra intersection. There it is, and there's our rule. With the probabilities, it works the same way, and so we can also say the probability of A or B is equal to the probability of A, probability of B, and again we have to take away that intersection. The other version of this is if we wanted to find the intersection and we had the union, we can rearrange this algebraically, so we can add that number of A and B and subtract the number of A or B, and we could rewrite this to be the number of A and B, the intersection, is equal to the number of A plus the number of B, subtract the number of A or B, that union. We do that for probability as well. So I'm hoping that makes sense. Now, what this does and why it's useful is this allows us to calculate without constructing. So if we like those abstract numerical approaches, that allows us to do it without having to draw it out and work out what's in each section. So that's our introduction. We'll now go through a couple of examples, and hopefully it will all start to make sense and come together. Okay, so the first example, we've got a spinning wheel divided into 8 sectors, each of which is marked with one of the numbers 1 to 8. So pretty easy scenario. We've got a spinning wheel, and it's split into 8 sections. 1, 2, 3, 4, 5, 6, 7, 8. The wheel is biased, so the probability of getting an 8 is equal to 0.3, while the other numbers are equiprobable, which means they're all the same. So that means that the remaining numbers take up that. So probability of not 8 will be 0.7. And because there's 7 numbers adding up, that means that probability of 1, for example, would be 0.1. So let's answer the questions. Calculate the probability of attaining the number 4. Because we know that the probability of 1 is equal to the probability of 2 all the way up to the probability of 7, they're all the same, then that means that probability of 4 would be that 0.7 divided by 7, and it would be 0.1. Now part B, if A is the event, the number obtained is even, we want to calculate the probability of A and the probability of the complement of A, which is not A. So our evens will be the probability of 2 plus the probability of 4 plus the probability of 6 plus the probability of 8. So we know that 2, 4, and 6 are all 0.1. So or we're adding them together. And the probability of 8 is 0.3. This adds up to be 0.6. That probability of an even is 0.6. And the probability of not A is obviously probability of odd, but it's easy to work out by saying that it's 1 take away that probability of A. So it's everything take away the probability that A occurs. So it's 1 take away 0.6, and we're left with 0.4. Complement should add up to 1, and so that kind of confirms what we're looking at. Now, of course, we don't have to take into account those scenarios where it can be both one or the other, because these are mutually exclusive, and that means that they happen independently. So there's no crossover between any Venn diagrams that include even and odd. Right, so there's our first example. It was just using our standard probabilities, but we built in some complements, and we built in a little bit of problem solving and thinking our way through the problem. All right, so second example, lots of words. So we've got a survey of a group of 50 people, found that in the past month 30 had made a donation. So 30 donate to a local charity, 25 donate to an international charity, and 20 had made donations to both local and international. So they're defining for us L and I, local and international, and we want to draw a Venn diagram. I'm going to draw a Venn diagram and a two-way table, just to introduce that. Okay, so we know that number in the universal set is 50. We know that the number in L, so the number of local donations, were 30. We know that the number of international donations were 25. And we know that the number, both local and international, are 20. So as a Venn diagram, we just have to be careful when we construct. So we know that the number in the universal set is 50. We've got our local, we've got our international. We know that the intersection is 20. And now we've got to be careful. We know that the local must add up to 30. So that means that missing amount is 10. So 10 plus 20 gives us our 30. We know that the international must add up to 25. So that means our missing amount is 5. So international adds up to 25. Now, if we add these three values, 10 plus 20 plus 5, we get 35. And that means that we've got 15 remaining that didn't donate. Okay, so constructing that Venn diagram, not so bad. We'll also do the same thing with our two-way table, so you can see that. Now, I know a lot of people trust the two-way table because it just becomes a matter of making sure that the columns all add up. And as long as you put things in the right spot, it's pretty straightforward. So let's go L, not L, and total. And I, not I, and total. Now, let's fill in what we have. We know that I and L is 20. We know that from the information 30 to go into the local charity, so L adds up to 30. We know the international charity was 25, so I adds up to 25. And our final thing that we know is that the total is 50. So if I fill these in, it's just a matter of filling in the gaps. So if this is 20 and it must add up to 25, the missing number is 5. If this is 20 and it must add up to 30, so we're now working vertically, the missing number is 10. Also, in the totals column horizontally, I have 30 and it must add up to 50, so the missing number is 20. And vertically, I've got 25 and it must add up to 50, so the missing number is 25. Now, the last number to fill in is the not I and not L. So it must add up to 25 and must add up to 20 simultaneously. 15 works in both directions, so that's how we know we haven't made a mistake. 10 plus 15, 25. 5 plus 15 is 20. All right, so both of these two things give us the same answer. So we've done A, we've drawn the Venn diagram to illustrate the results. In part B, they're asking us, one person from the group is selected at random. Using appropriate notation, calculate the probability that this person donated to the local charity but not an international. So our probability of local and not international. All right. So that means if we're looking for a probability, we need the number of local and not international over the number of the total sample space, or the number of the universal set. Okay, so our local and not international is 10, and you can see that in both. So that's 10 over our total sample space, which is 50, so our probability is 1 on 5. Okay, so it's nice and easy if we step our way through. What is the probability that the person in part A did not make a donation to either type of charity? So now we're looking at the probability of not local and not international. So that means we're saying it's a number of not local and not international, the number of the whole sample space. So that's our 15 over 50. And if we divide both by 5, we end up with 3 out of 10. And finally, part D, calculate the probability that the person in part A donated to at least one of the two types of charities. So at least means that it could be local, or it could be international, or it could be both. So really that's a tricky way of asking us for the union. So local or international. So that means we're looking at the number of local or international over the number of the total sample space. So in the Venn diagram, it's nice and easy, 10 plus 20 plus 5, so we've got 35 out of 50. In the two-way table, it's also pretty easy to see. It's just going to be the combination of both, only I and only L. So it's this top corner here, 20 plus 10 plus 5. And we end up, if we divide them both by 5, 7 out of 10. Okay, so hopefully that makes sense. That's a quick application into using probabilities with the Venn diagrams or two-way tables. And it's really just an adjustment. Instead of stating the number, we're dividing by the total sample space. Okay, so last example. So now we've got a scenario where we've just got probabilities. So we don't know what the numbers are, but we do know the probabilities. So again, we'll do it both ways. We'll construct a Venn diagram and we'll construct a probability table in this case. So let's do the Venn diagram first. We've got A and we've got B. We know that the probability is just going to add up to 1. We know what A and B is, so we know this middle here is 0.2. We know that the probability of A must add up to 0.4, so what's missing is 0.2. So 0.2 plus 0.2 is our 0.4. And we know the probability of B must add up to 0.7, so that means what's missing is 0.5. Now if we add these three up, we get 0.5 plus 0.2 plus 0.2 is 0.9, and we've got 0.1 remaining. Okay, so that allows us to then look at our scenario. We can also create the two-way table, or as soon as we go into probabilities, it's a probability table. So we've got A and not A and the total. We've got B and not B and the total. So we'll fill in now. This has to be 1. The total for B is 0.7 and the total for A is 0.2. And we also know that the probability of A and B is 0.2. So it's the same deal. We make it all add up. This must be 0.5. Did I write my probability of A incorrectly? Yes, I did. That should be 0.4. Sorry about that. So this must add up to 0.4, so we're missing 0.2. We've got 0.3 here to make it add up to 1, 0.6 here to make it add up to 1, and the missing amount is 0.1. Okay, so there it is. We can construct those Venn diagrams and two-way tables using probabilities, and now we can just answer what they want. They want the probability of not A or B. So that means we need to, from our table, work out what is not A or B. So the easiest way to go about this one is use our addition law, where we, all the way back up here, where we add the two things together and then we take the intersection of them. Okay, so that means I'll be saying that it's a probability of not A plus the probability of B, and I'm going to subtract the probability of not A and B. This out now all becomes quite familiar. Probability of not A is 0.6, probability of B is 0.7, and the probability of not A and B, which is only B, so not A and B is 0.5. So that means I've got 0.7 plus 0.6, take away 0.5, and we end up with 0.8. So the probability of not A or B, or the union of not A and B, is 0.8. Let's confirm that on the Venn diagram. So if I highlighted not A, it's everything except for A. There we go, a beautiful visual representation. Now if I highlight B, and that didn't help, I went over B, but we can still see all the probabilities. It's everything except for that 0.2 within only A, and that works out to be 0.8 as well. Okay, so hopefully that makes sense. The questions that you'll be looking at will be similar to these. I'll only set some of them because there's some different questions in this set that you probably don't have access to yet, and you should be able to work through quite comfortably. Thank you.